Hey, hi. Very good evening to one and all present here. I believe I'm properly audible to one and all, looking after me. Okay, so good evening once all, once again to everyone. And yes, thank you so much for this was actually a waiting part. Like we are also waiting for this live session, definitely. So very good evening once again, and I'm the Varsha, HR at Indian Cybersecurity Solution, and today we are going to have one of the best speaker which we have with years of experience. Introducing him, Mr. Debashish sir, Debashish Roy actually, with the years of 18 plus years of experience he's having with the basic networking, like networking in a networking proper domain, wherein today we took a very relevant and a very interesting topic where we are going to have him in this platform live session, definitely. And we are going to discuss upon something which is going to give us a great insights upon the topic, that is QoS in networking. So I would ask if we can go further with Devashi sir to come on the live stage right away.
Okay. Thank you, Kushma.
Yeah, hi Devashi sir, how are you?
Yes, fine.
Yeah, so basically sir, we all are waiting for this session, live session, definitely for so long. And this is, I believe, going to give a lot of insights and a clearance to the different people and the mindsets as well who's waiting for this. Okay, so I would ask you to kindly give us a proper kind of a knowledge where we are looking for. Okay, so I would
Yes.
ask you to take it up forward.
Okay. Thanks.
Yeah.
Let me share my screen. Okay. So today we are going to start with this quality of service. So this is a very interesting topic in our networking. So we are going to learn about the quality of service. What is quality of service? What are the tools required for quality of service? But to learn the quality of service, I think we should have some basic idea of IP addressing and the binary maths, because quality of service deals with some markings. And as you can see, that classification, marking, these things definitely I'm going to explain to you further. But first, let's begin our journey with a basic understanding of IP addressing. So this is our content introduction. What is an IP address? What is the classification of the IP address? And IPv4 in details, decimal to binary conversion, subnet mask, and a bit of subnetting also. So what is an IP address? So IP address, it is a, can say, a layer 3 address. It is a numeric address definitely, and it is an identifier for a particular resource in a network. Resource means in our case PCs. So the pieces can be numerous and they can be of the same color and the same cabinet, but the unique identifier that is in the network layer that we see in the OSI model, that is the unique numerical identifier for every device. That is an IP address. And yes, it is provided either by us, that is a private IP in a LAN, or it can be provided by the internet service provider or the ISP, that is a public IP. And IP address is of two types: IPv4, that is V4 version, version 4, and version 6. And you can see an example like 192.168.0.6. This is like the example of any IP address in decimal format, because we used to write IP address in decimal format, but IP address is in a binary. That is in IPv4, and definitely IPv6 is not in binary, it is in hexadecimal format. But we are going to discuss IPv4 only for now. Now, there is another address, that is MAC address, that is Media Access Control. That is actually the hexadecimal address, and it is a 12-digit hexadecimal number pointing to your NIC, that is Network Interface Card. Or what is NIC? It is a LAN card actually. So you can see the example of this MAC address. Actually, this is in hexadecimal format at the bottom of the screen. So the MAC address is a unique identifier of a PC, but it is a physical address. It is just like the IP that no two PCs can have the same MAC address, but it is a physical address, so you cannot change that. It is the burned in address that we say. So that is provided by the card manufacturer, the card vendor. Now, IPv4, it was developed by the ARPANET, and it uses a 32-bit address space, but 32-bit is not very long. And IPads is divided into four equal parts of octets, and each 8-bit group is known by octet. And IPv6, that I've already told you, it is the most recent version of the IP protocol, and it was designed by mainly the Internet Engineering Task Force, the IETF, because the IPv4 is now almost exhausted. So we have to come up with some new and very long address space. That is why this IPv6 came, and IPv6 is 128-bit long address space. And you can see total number of addresses is huge in IPv6 because we have a 64-bit interface or host ID in case of IPv6. As IPv6, as we know that there is nothing like network ID or host ID, but yes, the interface or host part is huge in case of IPv6 in compared to the IPv4. So you can see that at the bottom of the screen, that is IPv6 address. It starts from 200 something. It is known as the global unicast address, like it is a publicly routable address. So you have different addresses like unicast, multicast, global unicast addresses, unique local addresses. So different types of addresses are there, just like the IPv4. Now this is the IP version 4 header format. This is a very important part for your IP addressing. So there are many fields. There is a version. There is a header length. So that is the internet header length field. Type of service field, that is what we are going to discuss today. In the QoS, the type of service is a part of the QoS. And the total length of the header, then the identification, and flags. TCP flags are very important. That there are numerous flags in the IP header, because they say there's flags means whether the IP datagram is fragmented, that is, do not fragment DF bit, or more fragment, that is MF bit, that is in IP header. So if the IP datagram says fragmented, so in that case the fragment bit will be on. Otherwise, if it's not fragmented, do not fragment bit will be on. Then the fragment offset means that in the entire IP packet, say I am chopping the IP packet in different pieces. So fragment offset is that particular position where you are actually chopping the pieces. That is offset value in hexadecimal. Then the TTL, that is time to leave, means that it is used to prevent the routing loop, and every hop the packet travels, the TTL decrements by 1. And ultimately, if it reaches the destination, the TTL becomes 0. And as we know that in ICMP header, sometimes the TTL will find as high as 59 or 60 or higher than that also, maybe 110. But in internet environment, if you just trace out or ping any server, say any google.com server, you'll find that it is hardly 10 hops away. But TTL, we have to set it to prevent the routing loop so that the packet doesn't come back to the source. Now there is something known as protocol. What is that? This is the protocol number. As we know that there is a port number in transport layer, but in IP header there is something known as protocol number. So every protocol, IP protocol, TCP, UDP, these protocols have a specific protocol number which specifies their position or activity in the network layer. So port number, it is in the transport layer, and in the network layer you have the protocol number. Now we have header checksum, that is to check the integrity of the packet. It is like the, you can say, the CRC check in the data link layer. It is like that, just like that. Then the source IP and the destination address means the destination IP. And we must remember that if we are sending any data packet from any source to destination router, in the entire lifetime of the packet, in the entire journey, the source and destination address never changes. What is rewritten is the MAC address. So the source and destination MAC address in the Ethernet header, that changes, but in the IP header it becomes intact. So there is a 20 bytes and the other 40 bytes options. It is optional field. So that is not we are going to cover here. And also the data, that is up to 65515 bytes. So that is the IPv4 header fields. Then IPv4 has different classes, class A, B, C, D, and E. And you can see the range on the screen that the class A is from 1 to 126. Actually, it is up to 127, but 127 is reserved for loopback address that we use to test the LAN card. So range is up to 126. And you have the default subnet mask values also. Like subnet mask is something that is going to denote the masked and the unmasked bits, which are on and which are off. Like 255.0.0.0 means class A, you have the first part as a network part and all are hosts. And all bits of the network part is on. In class B, 128 to 191, class C, 192 to 223. So we use actually class A, B, and C. Because class D, it is reserved for multicasting. That is one to group communication, one to many communication. That is reserved for multicasting. And class E is reserved for experimental purpose. Actually, it is not used at all. It hasn't been used till now, the class C address. So we use generally A, B, and C, and yes, 127 to 127, 255, it cannot be used and it is reserved for loopback. That is to test your LAN card. Now this is the convert to decimal to hexadecimal numbers to binary. You can see that 0 and 1 is the binary number, and you can see the values from 1 to 128. And if you count this 1, those bits are on. You can see that 64, 16, 4, 2, this is on. So if you calculate, then the total is 86. And this is about the binary position. If you're having 4 bits, then say 0001, that is 0010. So if it is 0001, that is 2 to the power 0 means 1, then 10 means 2, 11 means 3. This way the bits are on, and you are having the corresponding decimal number like 1, 2, 3, 4 that I was telling you, and also the hexadecimal number. And remember one thing, that in hex we have up to 9. It is like the decimal. But if you say 10, it is A in hex, and 15 is up to F. So now I have converted an example of 192.168.0.1. That is the IP address in the decimal format to its binary equivalent. So you can say that all the 0 and 1s that is in the octet that we can see. Now, I've already told you about the subnet mask, that it segregates an IP address into network and host part. So you can see that in class A, first is the network part and 3 are the host parts. Class B, it is equal, and class C, you have 3 network parts, that is 255s, that is the network part, and last is the host part. And we have something known as classless inter-domain routing, where you have ISPs allocating the blocks of the IP address to you. That is known as CIDR value. In case of subnetting, you have VLSM, variable length subnet mask, that you are going to change the subnet mask because you are going to borrow the bit from the host part, and FLSM is a fixed length subnet mask that you have. Now, there is something very interesting known as subnetting, because if you are going to implement the IP address, or say you have created a virtual LAN and you want to implement that VLAN. So it is very much related to the IP addressing and subnetting also that you want to do. So how to do that? So it is a small example of the class C subnetting. So you have the 210.5.0 block of address, and you require subnet as a subnets, and you have to have the 30 host. So what you need to do, you need to calculate the subnet mask, the block size, the subnet ID, valid host, and the broadcast ID. So what you need to do, you have the formula as 2 to the power n. N is the number of bit that you have to take for subnetting. So you have to take the 3 bits because you need 8. So 2 to the power 3 is 8. So you just switch on these 3 bits and you get the sun mask as 128, 64, and 30, that is 224, because you already know the bit values that I have already told you from 2 to the power 0 to 2 to the power 7. And you have the summon mask, and the block size you get, that is 256 minus the fourth octet value of the summon mask, that is 224, that is 32. And you get the summit IDs as 0, 32. So it's increments basically by 32, and you get 32, 64, 96, this type of subnet IDs. Now it is a valid host part that it starts from 5.1, say for example, and it is up to 5.30, and broadcast is 31. Here it is 33 to 62, and broadcast is 63. This way, it comes in your class C subnetting. Similarly, in case of class B also, you'll see that the same type of calculation is there, and here you have the CID value as /18. So the default CID is /16. So 18 minus 16, you have the 2 bits for submitting here, and the total submit mask value is 192. That is 128 plus 64. So you have 255, 255, 192.0 here as a subnet mask. And the block size comes as 256 minus 192. Now there is a question, why it is 256? Why not 255? Because if all bits are off, the value is 0 in decimal, and if all 8 bits are on, the value is 255. Now you get the summit ID as 0.0, 64.0, 128.0, and 192.0 this way. And you have the valid host as 0.1 to say this is 64. So it goes up to 63.254, but the fourth octet cannot be up to 255 because 255 is a broadcast ID. So similarly, you get the 64.1 to 127.254, and the broadcast is 127.255 because the next subnet is 128. So this way you create the subnets, and class A is very similar to class B. So if we can do class B, I think we can do the class A also. So that is the part of the IP addressing. And now we will go back to the quality of service. So we were there in the quality of service, this QoS tools, and now we know about the binary match and the IP addressing knowledge, and we can do the QoS markings here better. So now let's start with QoS tools. Now, what is QoS after all? Why do you need QoS? That is the first question. If, say, for example, everything is fine in my network, every traffic is coming and going perfectly, do I need to implement QoS policy on my routers? No. But if I am facing some congestion in the network, say my bandwidth is low, my traffic is getting delayed, in that case, I need QoS. So there is a feature known as the delay. I'll discuss it after some time. So if the packet is getting delayed, it doesn't mean that there is congestion. It is a natural process. But if uneven delay is there, then the QoS is needed. So simply, QoS or quality of service is for congestion avoidance and bandwidth improvement. Now, how to do that? You have some classification, marking, queuing, shaping, policing, these things. So actually what happens that if the traffic is coming into your router interface. Say you have a router interface that is an ingress interface, that we say that is a incoming interface or the ingress, and the outgoing interface or the egress interface. Now, if the traffic is coming to the ingress interface, so what happens that if too much traffic, say if too much traffic has entered the router interface, so it will actually choke the interface. So you have to implement QoS. And classification means that you have to identify the traffic, the different classes. Now, what are the classes of traffic that you can have? You can have voice traffic, you can have video traffic, and you can have data traffic. Now, voice traffic doesn't mean only your voice. We know that the voice is also digitized, it is also converted to binary, but it is actually dependent on the, actually we denote VoIP traffic, VoIP traffic, voice over internet protocol traffic, when I say about the classification of voice traffic. And yes, we cannot allow all traffic to enter the router interface. So how do you know that the interface is facing the congestion? I will show you a bit later. Now, queuing is a method that where we are actually separating the packets, because we cannot allow all packets to enter at the same time, and we cannot allow that one queue will have the all packets, because definitely it will result in congestion. We cannot allow one big queue, that is not allowed. Okay. Now, shaping is policing is something that is to prevent the congestion or the congestion avoidance. Now, this is the characteristics of the network traffic. First is bandwidth, second is delay, then is jitter, and the fourth is loss. So bandwidth is the speed of the link. It is actually, bandwidth is like uh, according to the direction of the traffic. And say, for example, if I say 100 kilometer per hour, so that is the bandwidth. That is not the speed. Okay, we are actually sending 100 kilometer to a specific distance per hour. That is the bandwidth. And what is FIFO? First in, first out. So packets are served on a first come first serve basis. So it means that say in case of QoS, if there is no QoS, then packet is actually served as they come to the router interface. So if they're coming at first, then it will exit first. But yes, if you implement that and do not implement any QoS policy, then any traffic can come and it may result in congestion. Okay, so now it's delay. So I want to show you the response from the ping protocol to actually show this delay and jitter. Say, for example, go to CMD and I'm pinging, say google.com, and you can see the response is coming. You can see that that is packet size is 32 byte, and time you can see that it is even time, almost even, 40, 44, 40, 40 millisecond, and TTL value you can see. So this time is a round trip timer, means my ISMB echo packet is going to the server google.com and it is coming back, and that is a delay. Yes, definitely it will take some time. So definitely there's a delay time. That is not the feature of any congestion. It doesn't mean that my network is facing any congestion. But if say this time, this round trip timer gets incremented, say 40, 44, then 46, then 50, 54. So this time is getting incremented. So in that case, you can say that there is uneven delay in your network. That is bad for your network. It means that there must be some congestion in a network because you are getting that uneven delay response. So in that case, that is a jitter. So if you are facing any jitter, then you have congestion in your network, and you should implement the QoS policy. So delay is a one-way delay, and delay can be caused by processing delay. That is when the router does the routing, it should see the ARP table. As you know, that if there are different routers there, then definitely it should actually check the ARP table of the other router. So, say for example, this is a router, this is another router. So the ARP broadcast is sent to this router's interface, and this router actually sends an ARP reply. So for that request and reply, you have the processing delay. So it's normal. Queuing delay is also there. The amount of time a packet is waiting in a queue, or you can say the latency time. The latency, so the packet is actually waiting in the router scheduler to enter the queue, to enter the router. So in that case, that is a queuing delay. Now that is serialization delay. It takes that to send all bits of a frame to the physical interface one by one serially. Propagation delay, to bits to travel through a 10-mile fiber optic link. It is much lower than the time it takes for bits to travel using satellite links. So that is the physical medium, through physical medium when it's propagating. So in that case, so we know that the LAN speed, the speed or bandwidth of the LAN is much higher than the WAN speed. Definitely, because in case of WAN, you can have several miles away, several kilometers away. You can have a 10 gig link also. But if you are having a best possible link according to the bandwidth, but still the distance is long. So you have to propagate, you have to travel a long distance. So that is propagation delay. Now that is jitter that I was talking about. That jitter is increasing. Say first is 20 millisecond, then it is 40 millisecond, then the delay between the packet 3 and packet 4 is 5. So actually what's happening, it is uneven, it is erratic delay. So that is the example that your network is facing congestion, and you should have the QoS policy implemented immediately. Say an IP phone. IP phone is dealing with the voice over IP packets, and about those voice over IP packets, say VIP packets is there, and you are facing this type of congestion in the network. So in that case, what you will do, you will just implement QoS policy. But if there is no jitter, if there is no congestion, then definitely no QoS policy is required. Now, to proceed further, we'll discuss the three categories of quality of service. Now, there are three QoS mechanisms. One is best effort, then it is diff serve, and the other is, here it is not written, but it is int serve. Now, best effort means that there is no QoS restriction. Any traffic can be in the FIFO format, first in, first out. So any traffic is entering the router, and the router is sending the packet according to its best effort. So actually, there is not no restriction, not a strict policy, and it is actually no QoS at all. But yes, Cisco has included it in the QoS, so I can say that best effort is also a QoS, but it is actually not that. Deep serve that we use, that is less restrict policy. Deep serve means that, say you are running different protocols. Say we're running a multimedia application and gaming application, an IP phone, a VoIP application, and you are having the, say, video conference. But now you have ended that. That is finished. So that video application has released the bandwidth. So that bandwidth can be given to other applications. So you can actually share those bandwidths. So that is deep serve. So it is less restrictive, and you can share the bandwidth to others. So that is implemented nowadays. But in serve, it is something that is very strict. it says that okay, the video conference may have ended, but I will retain that bandwidth. That video application will not release the bandwidth to others, or it will not share the bandwidth to others. It is a very restrictive policy, and it's known as int serve. And we have a certain protocol for this also. I can tell you that is RSVP protocol for this. Cisco has developed resource reservation protocol for this int serve. So that is something that we should avoid. This is so much restrictive QoS policy. Then you can see in the figure, all traffics are coming, all the input traffics are coming. Say in red, it is high priority packet, violet or purple is denoting medium priority, and black is low priority. All the traffic is coming of all the priority levels, and then it is entering the router interface. And you can see that these are the different queues. This red packets are in a queue, this is purple packet queue, and black packet, and it is getting output. So that is the queuing. Queuing means that you have different say containers. You are making different say containers. Say this container is for best effort traffic. This container, it is for VoIP traffic. So you are actually making different queues, because if you do not have these queues, what will happen? Say you are having only one container and you are pouring the best effort VoIP any traffic, and definitely that queue will be filled soon and it will overflow. So the data will be lost and it will result in congestion and it will overflow. So that it doesn't happen, you have these different queues. Now you have this quality of service classification. So what does classification mean? Classification means to identify the different types of traffic. So you are having packet 1, packet 2, packet 3. These all packets are entering the switch or router, anything. And now you have to classify it with class 1, say voice traffic, class 2, video traffic, class 3, data traffic. So what you have done, you have identified the traffic. So the router or switch, a device first identifies the traffic. That's the classification, because say in a street it is having a huge type of traffic jam. Now you should identify for which type of vehicle are you having this traffic jam. So that is a classification. Okay. Second is marking. Marking means to prioritize the traffic. Means you can say that packet 2 has given the DF, that is a best effort marking. Packet 1 is CS5 class of service 5, CS5 for broadcast video. Packet 3 EF, expedited forwarding. CS7 class of service 7 for network control. So you are actually giving some priority to different traffics, because see, you cannot allow all the traffics to enter the router interface at the same time. So we have to prioritize the traffic with marking. And now we should learn marking in details. Say that is the 802.1q frame or the .1q frame. You have the tag control information or TCI bytes there, and you have the priority and CFI, canonical format indicator, and VLAN ID. Now, what is CFI? It specifies either Ethernet or token ring fields in the VLAN. And VLAN ID, it is, we know that 12-bit VLAN ID is there. So you have the actually 2 to the power 12, that is 409 VLANs. Now, this QoS, that is class of service marking. So what is QoS marking? It is used where? It is used in switching, because it is the layer 2 marking. We have something known as layer 2 marking, and we have something known as layer 3 marking. Layer 3 marking is known as, it is used in routers. Now in class of service, we have 3 fields, only 3 binary bits. So we have already done binary. So say binary bits all 000. Say 3 bits are reserved for class of service. This is a very old marking method. Then you have the layer 3 marking strategy. There is an IPv4 packet. You can say there is a field known as TOS, toss byte, or type of service in the IPv4. And here, these 3 fields, 3 bits, 1, 2, 3, that is known as IPP marking, IP precedence. And it is totally backward compatible with COS. Can you see? Because IP precedence is also 3 bits long and the COS was also 3 bits. But in these 3 bits, how many we get? That is 2 to the power 3, that is 8 markings. So that is not a very good marking. That is a very small marking actually. So later came DSCP, Differentiated Services Code Point, where you have the 6 bits means 2 to the power 6, that is 64 marking. So actually it increased from 8 to 64. And you know what COS value, if we get the 0 to 7, all these COS values, but Cisco reserved the 6 and 7 QoS values, the COS values. So we actually could use 0 to 5. So that was a limitation also. So still, if you get 8 bits, that means 3 bits, there's 8 values, but that is not enough. So IP precedence is not used anymore now. It was replaced by DSCP because DSCP has a lot more markings. We need to have a lot more markings. Okay. Now you can see that these are the different markings that we have. It starts from CS0 and 0, 1, 2, 3, 4, 5, 6, 7. And you have something known as PHB, that is part hop behavior. So what is part of behavior? Cisco has specified different standards according to the COS value, COS markings. Like CS0 is for class default class. So it may be that there is no congestion and no QoS at all. Like this is like the best effort. You can say unclassified specific traffic, IPv6 and broadcast traffic. Now, what is scavenger? Scavenger is like your gaming traffic or YouTube or point-to-point traffic. Say we're running any YouTube applications, that is a scavenger class. Bulk data is for CS2, part of behavior, COS marking is 2. Now comes the critical data. Say any web server, you are running any web server, email, LDAP, or CRM application, then it happens AF, assured forwarding. AF21, multimedia, AF41, video conferencing, okay, CCTV streaming. VoIP gets EF or expedite forwarding. Now, expedite forwarding is something that is done by the service providers. We do not set the EF markings. We set the AF markings because VIP is for Jabber, telepresence, Cisco IP phones, and it is normally managed by service providers. Now, CS6 part of behavior is equals to COS value of 6 and 7 used for traffic class network control, and it is used for routing protocols. As you can see, the BGP, EIGRP, OSPF, HSRP, load balancing protocol, NTP, network time protocol, PIM, that is a protocol independent multicast of the multicast, and IGMP, also multicast protocol, internet group management protocol. Now, these traffic classes can be how many traffic classes? Cisco is saying that you can have more, not more than 11 traffic classes because every traffic class is special and it is unique. But if you are saying that I'm having, say, 20 or 30 classes, everybody is special. It means nobody is special. So Cisco is actually limiting the traffic class into 11 classes. Now, these are the marking values of this class of service. That is DSCP class selector names. We call this class selector and CS marking. And then you can see the binary DSCP values and the IPP binary values, that is equivalent. I have told you that class selector is equivalent to the IPP. and default is CS0. Binary DSCP, you always remember one thing, that in case of CS, the last three these bits are always 0. Say 001, 000, 010, 000. So always the last three bits are always 0. And the IPv binary values, you have the 0, say 1, 2, 3, 4. This way it is incremented in IPv. So IPv, we are actually having the first three binary values. So we already know the binary now. So that is the binary equivalent of the IPv. And binary of DSCP, you can have all the 8 bits. So there is a class selector, values from right away from class 0, CS0 to CS7, those 8 bits. And the names for the IPP is very important. Routine, priority, CS2 is immediate, CS3 flash, CS4 flash override, CS5 critical or critic traffic, CS6 internet or control, and CS7 network control. So say internet or control means some routing protocols. And so for every activity network traffic, you have these names for the IPP. And now that is the AF, or the assured forwarding values. Not only class selector, but there is a AF values also. Now in case of AF, that is class 1, class 2, class 3, class 4. There are 4 classes. And there is a low drop probability, medium drop probability, and high drop probability. Now, what is this? We are actually deriving these values in 4 classes, and in each class you have these 3 values, so total is 12 values here. And AF 1, 1, 1, 2, 1, 3. So 1 means what? This first one is a class 1, first class, and 1 low drop probability, 2 medium, 3 high drop probability. Similarly, in class 2, 2 1, 2 2, 2 3. Class 3, 3 1, 3 2, 3 3. And class 4, 4 1, 4 2, 4 3. Now, there is a specific binary match behind this. Now, if you convert 1 1, say for example, it will be 1 0 1 0. And if you convert it in decimal, it will be 1010, means 1248. Now 8 plus 2 becomes 10. Like 2 1 means this one, 2 means this 0 1 0. You see, you have to divide it in 2 parts. First is like 0 0 1. 0 1 0. 0 1 0 means 2 to the power 1 means 2. And 0 1 0 is like this. But this last bit, 0, is always reserved. This last bit is always reserved. So it's actually 1, 2, 3, 4, 5. 5 bits. Like 0 1 0. 0 1 0 means 2 to the power 1, that is 2. And 0 1, that is the 1. You are not taking this last 0. Like a 3 1, that is 0 1 1, means 1 and 2, 2 plus 1 3, that is in binary, and 0 1, that is 1, that is 1. You are not taking the last 0, that is always reserved. Now if you calculate the decimal number, say 001010, if you take in account all the bits, say what happens? 10. Here 1 2 4 8 16, 16 plus 2 18. So we can convert these AA values in decimal as well as in the binary format. So if somebody gives you the binary format, you can convert it in decimal and vice versa. So these are the AA values, very important. And probability of dropping means the traffic that is in this low drop probability in 1 1 2 1 3 1 4 1, they will not be dropped much. It's very little chance that they will be dropped much. But medium drop probability, all are same in the medium drop probability. It doesn't mean that class 1 will be dropped first or class 2 will be dropped first. No, all are equal in these categories, in this column. And high drop means everybody is in the danger of high drop probability. So any traffic that is marked with this high drop probability, it can be 1 4, it can be 2 2, anything. It can be 3 0, it can be 3 8. All are having the same priority, means the same level of, say, same danger level, that they can be dropped anytime. So that is the assured forwarding, or A values. And when we prioritize the traffics, we can do it in the Cisco modular QoS, that is CLI mode, or there is something known as NBAR, network based application recognition. There we can actually mark these traffics. So for marking these traffics, we use these markings. So that was the marking part. That's very important. Next is queuing. Queuing, that I've already told you, that's the buffers in network devices store the packets. So in the router scheduler, the traffics are waiting for their turn to enter the route interface. There is a queuing, that you are having different queues and you are giving priority to some traffic. So that is entering first, followed by other traffics. So the traffic can then be processed at a later time once the interface or bandwidth becomes available. So you are actually waiting the traffic in the queue. You are keeping the traffic in a waiting state. What are the queues after all? What are the types of queues? There are two types. There are several types actually, but the main is CVWF queue, class-based weighted fair queuing, and priority queues, or PQ, or low latency queue, LLQ. So, what is class-based weighted fair queuing? Now, it is intended for non-time loss or jitter-sensitive bulk and transactional traffic. Now, it is going to specify a reserved bandwidth. What does it mean? It means that in case of class-based weighted fair queue, we are dividing the traffic into different classes. What are the classes? Same: voice, video, and data. And we are actually giving a certain amount of minimum bandwidth, minimum assured bandwidth. So we are saying that any traffic, say voice or video traffic, is getting minimum of, say, 1 GPS bandwidth, and maximum can be 2 GPS or 4 GPS bandwidth. But we are actually reserving the minimum 1 GPS bandwidth. So that is the weighted, means what? Weight means the priority, the bandwidth we are reserving for every class. That is a minimum threshold that we are having. And priority means we are favoring only one traffic. Say we are favoring voice traffic, and even if there is congestion, voice traffic is getting processed first, and there is every possibility that voice traffic will take the entire bandwidth and it will result in too much congestion. But that is the LLQ, or the low latency queuing, or the priority queue. Low latency means that the traffic is not going to wait at the router interface for a long time. Now, in the diagram, we can see that how to prioritize the traffic type. Bottom, you can see the class default, that is in the weighted fair queue. But if you're using LLQ, low latency queue, this is the priority. This is the, say, the voice traffic is giving the highest priority, and you can have different queues there. One can have bulk data, critical data, network control, and call signaling, and all the bandwidths that you can see, that is for the queue. But there is a misconception, that is, these queues are getting only this much bandwidth. This is the highest bandwidth that this queue is actually allowed. No, that is not. It is actually the minimum guaranteed bandwidth. So when we are seeing that network control that is greater than equal to 1 Mbps, so what we are seeing, or what we are going to say, that is, you are having at least 1 Mbps or bandwidth. You can have more also, but at least 1 Mbps. But I am not limiting it to 1 Mbps. But as you can see in the priority queuing, it is always less than equal. So priority queuing means that yes, you can enter the interface at any time, say voice traffic, even if there is congestion, but I'm limiting your bandwidth to some extent. That is, either you enter at 3 Mbps or lower, but not more than that, because otherwise the entire network will be down. So that was the queuing, that you are waiting or keeping the traffic in the waiting stage. And now we should discuss two more congestion avoidance methods. It is not the queuing method, but the congestion avoidance, that is shaping and policing. Shaping means it is allows to manage the traffic flows, and it is a bit less restrictive policy. Now, if there is congestion, say a packet is coming at a higher rate, now the shaping slows it down, and it tells the traffic that you are moving too fast, so you should slow it down voluntarily. Otherwise, yes, I can drop you, but I'm requesting you to slow down. And you can see that there is a graph also, that the traffic is coming and there is a time in the x-axis and the y-axis, that is traffic. And you can say that it is actually in a constant rate, the traffic rate is there. So traffic shaping is not dropping any traffic, it is keeping the traffic in a waiting stage, but it is not dropping any traffic, it is slowing down the traffic. So you can say that, say, buffering happens. You are, say, seeing any this YouTube live and some buffering happens. If it happens, then that is for QoS policy traffic shaping. But if it's policing, then what will happen? You will not hear or see anything, because then the QoS will drop that traffic. But we do not do the policing naturally, we do shaping. Now, what is policing? Policers are normally configured on the service provider network to discard incoming traffic that exceeds the line rate. So, policing, it is a very restrictive policy. But what enterprises normally do is shaping the traffic. The shaper slows message down by giving the message that I have already told you. But in service providers, if they implement policing, so traffic policing controls the rate at which incoming data packet arrives. And most traffic policing configurations send traffic that falls within the policy rate. And when it exceeds the policy rate, then it's dropped. Say I've implemented a policy map. So you implement QoS with say modular QoS in CLI, creating class map. Then you implement policy map. Then say you have restricted it to 4 Mbps, but it is taking 10 Mbps. So in that case, policing will totally discard the traffic. You can see in this graph, it's clearly visible that is how restrictive it is. So you can see that in these areas, these townside areas, it is absolute just throwing away the traffic. So it is throwing away these traffics. But in shaping, that graph was constant in a straight line. So it is not actually keeping the traffic in waiting stage, but it is actually discarding the traffic. So traffic policing, maybe it is a very strict policy and it is not to be followed. Now there is something known as RED, and random early detection. Later, Cisco developed it with WRED or WRED, weighted random early detection, and it is related to tail drop. Now, when WRED, I'm going to discuss a bit later, but when it is not specified, this is a default congestion avoidance method, and it treats all traffic equally, and it doesn't distinguish between the service types. So tail drop means what? That I'm not going to consider any traffic as important. If the output queue is full in the router, so what happens that any traffic that is coming, it is prone to be dropped. Packets are dropped until the traffic congestion is cleared, and I do not care if it is voice traffic, video traffic, or data traffic. You can see that this is the interface output queue of the router, and new packets are coming, and they're getting dropped right away. I have no idea whether that is voice, video, or data. I'm just dropping the traffic. That is a tail drop. Tail means this traffic that is in the latter part of the queue it's getting dropped right away. Now let's talk about weighted random early detection, or the WRED. And it keeps track of the average queue depth. So when the queue begins to fill, only a few random packets will be dropped. So it means that it actually maintains a queue length, means it actually maintains a certain level. That if you were inside a certain level, say you are inside, say 20% of the congestion level, you will not be dropped. If you go beyond that, it will drop. Say for example, if I say, if you are moving too fast, if you are moving within say 100 kilometer per hour, well, you may not be dropped, but if you go beyond that, you can be definitely dropped. So as the queue length grows longer, it becomes more aggressive, dropping even more random packets until it reaches the limit. So if you cross that barrier, then WID is like the tail drop. Then it can drop any traffic, but tail drop actually drops every traffic. But WID maintains a certain weightage or certain level, and if you go beyond that, then it will drop, but not before that. Say say this is the same picture, but now here there is a threshold, minimum threshold and maximum threshold. So if you are inside the minimum threshold, say, then you will not be dropped. The minimum threshold and maximum threshold, if you're between that value, then it will drop random packets, and there is a chance that your packets will be dropped, but it is not a high chance. If you are inside minimum threshold, nothing will be dropped. If you are within this minimum and maximum threshold, yes, there is a chance some packets may be dropped. But if you go beyond that maximum threshold, all packets will be dropped, and it will be like a tail drop. Then it will drop randomly any packet. So with WIDD, the packets to be dropped can be manually specified using traffic weights, which are indicated by the IP precedence or DSC values. Packets with lower IP values are dropped more than the packets with higher IPP values, that we have already discussed these values. And the IP explicit congestion notification ECN bits can be set using WRED. It specifies the congestion during transit. So ECN bits are the last bits, the last in the 8 bits in the DHCP, last the 2 bits are reserved for the EC notification. So those bits signifies the congestion during transit and will tell the ECN cable endpoints to reduce packet transmission rates. Now, at the end, that is a QoS configuration. So we can actually implement the QoS policy also in our router switches, but nowadays QoS is not implemented in this modular fashion in CLI manner, or in CLI mode, should I say. It is implemented in automated way. So in automation, you are making actually scripts to implement QoS, but we are not going to do that here. We are not making the Python scripts or JSON scripts. We are implementing CLI. So what you do in the router or switch, you make a class map. So in class map, say I am going to implement QoS for anything, say any SMTP or voice or FTP traffic. So the class map, say class 1, and match is matching an access group 101. So actually we have configured an IP access list which is allowing some network. So that is the access group. If you are configuring any ACL, then you will do this match access group, or it can match any other thing, like it can match the SMTP or any protocol. It can match the access group, means ACL, or it can match any other configuration. Here we are matching the access group, and then we are creating another class map class 2, and we are matching another ACL, that is 102, and in that ACL you just allow the traffic. Say you have specified extended ACL, and here from source to destination we have allowed the HTTP traffic in the 101, and in case of 102 you have specified the SMTP or FTP or any other traffic. So that is a class map. And now you're going to implement the policy map, or you are going to implement policy one, that's any policy map name. And then you specify class map with class and then the class one. So you go to the policy map and you specify class and give the class name as class one that you have already specified. And you are, say, limiting it with bandwidth. So you are setting bandwidth with 3000 say bit per second. You are limiting with in the bandwidth 3000 bandwidth within that. You can do anything. You can actually you can set many things. You can set bandwidth and you can set other parameters also. You can set priority in case of, say, example, voice traffic or any other traffic. But I'm setting, say, bandwidth and queue limit. I'm setting the queue limit also. And similarly, in class 2, I'm limiting it with bandwidth 2000 bit per second. So one traffic, say HTTP traffic, is limited to some bandwidth, say 3000, and the FTP or semi traffic or any other traffic, say voice traffic, is limited to the 2000 bit per second. And now to implement the QoS policy, you go to the interface, say gigabit Ethernet 0 by 4, any interface. And what is the syntax? Service, output, and policy, and then the policy map name. So this way you can actually implement the QoS policy. So this is the syntax for the QoS, but I can show you the modular QoS in this Cisco packet tracer also. So let's jump onto the configuration here. And I have some routers. All the routers, actually, they do not support the QoS because QoS is a advanced model. But say I'm taking this 2901 routers. Other routers, some routers may support it, but some may not. It depends on the IOS of the router and switches. So you go to the router. Go to config mode and create a class map and give a word. Say, or you can give a word, or you can say match all. So it may match all traffic or match any, or either and or any operation. But I'm giving a word, say class map, say CSS, and then match. And you're having that access group that I've already told you. If you're just setting the access list, then you will implement it with access group. Or if you implement any, then it will result in matching any traffic. Or you can implement a class map here, COS value, destination address, or even many things are there. Say a protocol. So I'm, say, matching any protocol value. Let's say protocol, give a question mark. Say you are having all these protocols, right from this RPGP, all these protocols are there. And I'm, say, matching anything, say SMTP, this SMTP protocol. So this is a class map that I've created, but this is only the class. I can create different classes, another class with HTTP traffic I can create. But say I'm going to create a policy map next. So if policy map, policy-map, and then word, say you can have the policy one or any string, any word. Press enter, and then you specify class. And what was the class? ICSS. So you specify the class inside that policy map. And now what are the things you can do? You can just keep question mark, and you can set the bandwidth, you can set the priority. Say you are setting a strict scheduling priority for this class. Say any HTTP traffic or ICMP traffic, any ping traffic, or say any voice traffic, you can do that. or I'm here. You can implement shape also, traffic shaping, or you can set the different QoS values also, or set IP specific values or IP precedence values. Here I'm showing you these things. You can see these values: critical, flash override. So you can set these values that we have already discussed, IP precedence and DSCP values. Or also you can set the priority priority. So it can be in percentage also, or it can be in kbps, kilobits per second, or it can be bandwidth. So we can also restrict the bandwidth, say that is in kbps, kilobits per second, like 3000. So I'm restricting the bandwidth of the SNM SMTP to 3000 kilobits per second kbps. So you can do many things in this modular QoS, and this is a way to configure the QoS, and then exit, and now go to the interface. This interface gigabit 0 by 0 this way, and now you implement how to implement. You implement it with this service policy, service hyphen policy, and now input or output, assign policy map to the input of an interface. So if you want that to implement that policy map to your ingress interface, that is the incoming interface. If you want, then you will do it in as the input, and if you want to implement it in the egress interface, so you will implement it as the output. So say I want to implement it as output. So if my router is actually sending traffic to some other router, to some other network, so it's going to implement it in the egress interface, the outgoing interface. And if somebody is, say, sending me the SMTP traffic or any other traffic, then it is going to implement it in the ingress interface. So you give the service policy output, the question mark, and the policy map name, the word it is was. So you say policy one. Now the router is going to implement that policy map whenever it is going to send any SME traffic towards a destination. And can I view the show QoS policy? Show QoS, but I think in packet tracer, let me check. Yes, you can see the policy map. You can now see the policy map. You can see the queue. So you can see the show policy map. So here you can see that this policy map, this bandwidth is implemented, and is already giving a threshold of 64 packets. So we haven't sent any SMTP packets, but in a demo purpose, say it is showing you that it has matched the 64 packets. And you can have the queue also, but show queue, and it is the gigabit 0 by 0. And so it is actually showing you the queue. Class-based queuing is there, weighted fair queue, output queue, and you can see all these thresholds there. So it is actually giving you a demo output in this packet tracer. It is not giving you the actual output of the size, maximum, total, a threshold, and the packet drops. It is not showing the real thing because it's a simulator draw. But at least you can implement the QoS policy, the class map, policy map, and you can also configure and implement the service policy in the interfaces. So this is how you going to configure the quality of service. So quality of service that we have discussed so far, this is a very important part for your network to actually avoid the congestion. And there you have different types of strategies that we have already discussed. The prioritization, that is marking. You have to first mark the traffics, and then again you have to queue the traffics in separate queuing. You have the class specified fare queue. Previously, you had the weighted fare queue only. So the classes were not so defined, but Cisco later defined it in the CBWFQ manner, class specified fare queue, and you have the different queues for that. And then in the router scheduler, all the traffics are waiting to be routed or to enter the router interface. And then you have different type markings like this COS and IPP. COS is a layer 2 marking, IPP and DSCP is a layer 3 marking that we have discussed. And then you have the two congestion avoidance mechanisms like shaping, that is going to slow down the traffic, but it will not discard the traffic, and the policing, that is a residue policy in case of the ISP level that it discards. And in ISP, you must have seen that, say you have purchased net pack or something like internet pack, say 3 GB per day download is allowed or 2 GB per day download is allowed. Everybody uses that. Now, after the 2 GB download, what happens? Your speed drops suddenly. Say you are using 5G and your speed drops from 5G to 4G even to 3G. Now, how does it happen? Does anybody monitor that in the ISP data center? And they give some commands when you just fill the capacity of your data usage? No, it is implemented by default by the QoS policy, and nowadays that I've told you, it is in scripting, in automated way in automation. Previously, it was done in a scripting manner, but it was very difficult to manage all these devices because there are tens of thousands of devices. So how can you manage those QoS manually? So these things that we have discussed, and I have also shown you the practical implementation that is also available in the packet tracer or any other simulator. So you can actually see a demo how to implement the QoS on any traffic. I have shown you in SMTP. You can implement it in any other traffic, say any HTTP traffic, voice traffic, or the ISMB traffic that you can implement. So this is a practical thing, and the theory part we have already discussed. And also at the beginning, I have discussed about the IP addressing that is very much related to your QoS, because the binary maps are related to the QoS. As you can see, as you've seen the QoS markings, that can be converted to the binary values, and then it can be converted to the decimal as well. So the IPP, DSCP, these values can be converted to binary. So binary is very important, binary maps for QoS. So this was about the QoS. That is a very long topic actually, and it covers CCNA and CCNP both. It was a very big topic in case of CCNP. Still, it is a big topic, and it is a new introduction in the CCNA 200301 syllabus at QoS, quality of service. That is a new topic. So that is a very new topic in the QoS that we have discussed, the theory part and the practical part both. So I hope that it was really helpful for you to gain large insight about this topic. A bit hard topic, but it's not hard at all. It is, if you know that topic, then it is very much easy to handle this topic. So I hope it was informative for everybody, and I hope you to see you again in future with some new topic. And thanks for joining this masterclass on QoS. And I will come with some more topics, and so I hope that you will join there also. And till then, it's bye.
Hello. Hello. Yeah, I believe like sir has already done with his part basically. So I believe once again that everybody has really like got a lot of information and insights from the sir's end only. Okay, so definitely you can be and stay tuned with us, the Indian Cybersecurity Solution. You can find out that we are providing a lot of these kinds of insights in the coming days itself, in these kinds of workshop, webinars, seminars, as well as live. Okay, so you can connect us and you can find that the like it's visible at the website and the email IDs as well as the numbers. If you want, you can connect us anyway for all these further informations. Okay, so thank you so much all, and we hope that we are going to come back once again with a lot of these kinds of insights and workshops, or I can say lives, with these kinds of faculties and the great speakers among us. Okay, so thank you so much once again, and stay tuned with us. Thank you all. Thank you for this great session. Thank you so much. Yeah, thank you.